Okay, I guess I don't have to speak into that one. Next, Chris Pinella is going to talk to us. He is a regional air quality modeler at the Utah Division of Air Quality, and he's going to talk about how the Great Salt Lake and changes happening there might affect air quality. Chris.
Thanks, Seth. Yeah, I'm not Derek Mallia, and that's what's on your agenda. And unfortunately, this is his presentation, but he had a family emergency that kind of pulled him away at the last minute. So I'm happily here to fill in and present this work to you. Thank you. So the title of the work is The Impacts of a Shrinking Great Salt Lake on Future Air Quality Along the Wasatch Front. Now, it would probably be a bad idea to drain the lake in physical reality to kind of measure what would happen. So how we do this, how we address this is through modeling. And in particular, we want to kind of focus on kind of these short-term dust events which kind of come in and blow through the Wasatch Front in the springtime and actually increase PM2.5 to quite large levels. It might surprise some people. So what do we know about the dust along the Wasatch Front? Well, windblown dust can have a wide range of impacts that include, as I mentioned, air quality. Now, kind of focusing on that, again, these episodes are quite short in duration, maybe only on the scale of an hour or two. However, again, on an hourly basis, PM2.5 can increase quite a lot, sometimes over 300 micrograms and sometimes during these episodes. And also, not only just air quality, we talk about visibility impairment too. I mean, there's oftentimes a lot of accidents that occur during these kind of really brief but severe dust storms that kind of blow into the valley. So unfortunately, it looks like dust. This problem is not only going to be getting worse in terms of magnitude, but potentially even in terms of frequency. In fact, it looks like some of these trends have already been observed across the southwestern United States already. So here's a kind of a picture of the lake, and the white outline kind of shows what the lake might have looked like, maybe back in the old days, maybe mid 19th century or so, the extent of the water. But these days, it kind of looks like, if you look at the satellite imagery, you can see that right now there's actually quite a lot of more exposed lake bed than there has been in the past. In fact, 50% more. And this is kind of what we're looking at here. This is actually 2015 satellite imagery. And I want to kind of point out the Bear River, which is just north of the Salt Lake. So what these numbers represent is kind of how much of the water inflowing into the lake does this particular river contribute. So for example, the Bear River itself contributes more than half of the water flowing into the Great Salt Lake. So we're going to talk a bit about later about what might happen if we were to actually dam that river. And here I kind of want to focus on the bottom plot here on panel C, and that's actually kind of just a depiction of lake elevation. These measurements have been taken from, looks like the mid-19th century here at Gilbert Bay up until the present day. And as you can see by the kind of linear maroon line that, the lake level is actually going down. No surprise. So, kind of in lieu of the fact that, we do have these kind of severe air quality concerns during these brief periods, and we also have these visibility impacts, it might be important to kind of, come up with a model that could actually be used for forecasting. For example, we already have kind of the AQI, kind of our PM2.5 24-hour, forecast, but what if we took it a step further and was able to do kind of an hourly forecast, kind of a near-term forecast of dust events? That'd be really exciting and really useful. You can imagine, UDOT signs kind of showing, warning, get off the road, dust storm coming in, things of that nature. But what would need to happen first is we need to identify where the actual dust is coming from, So we have a good, we talked a lot during this conference about wind data and transport, but it's also, we need to know about the land type, the soil type. So, if we can actually do that, then perhaps we can actually create or construct a successful model. And with this model, not only can we use this for forecasting purposes, but, maybe we can also see what would happen if, things keep going the way they're currently going. So this is kind of a conceptual framework of the model. And here we have two components. We have the WRF meteorological model. Tring just talked about that in the last talk. Now we have this other model called STILT, which stands for the, well, I'm going to mess it up. I'll try. Stochastic, I'm going to cheat, actually. And the stochastic time-inverted Lagrangian transport model. So STILT. So it's very similar to high split if anyone's used that in the past. It's kind of a trajectory model, kind of with some extra stuff, which makes it appealing for this kind of work. So how this works is we're going to go backwards in times from a receptor site. For example, this could be a city. For example, take Salt Lake City. We'll go backwards in time and look at at how or where things came from. And the way it does this is through, again, a stochastic or statistical randomness, kind of an ensemble approach to kind of capture more accurately, how wind or transport can occur. So the way dust works, if you look at the equation down there, it's basically what that says is that when the frictional velocity or the wind across the surface gets high enough or greater than what's called the threshold velocity of the soil, then there's going to be uplift of that soil and hence transport. So I just want to point out before we get into technical details, because I'm probably not going to do this material justice like Derek might have, but there is a paper that Derek just published in October 2017. It's in the Journal of Applied Meteorology and Climatology. And it's a really great paper. So I encourage anyone who's interested to come go check it out or come see me for more information. So this is kind of a look at what STILT kind of looks like. And what we're looking at here is this 3D imagery. The dots kind of represent air parcels. And this isn't related to the dust modeling that will be shown here today, but it is related to the idea of this transport. So the colors of the particles represent the age of the particles, how long they've been kind of in the air. And Salt Lake City is depicted there as being kind of this receptor site. The mountainous terrain around Salt Lake City is depicted here. And so basically these backward trajectories, they're dispersed via this turbulence within the planetary boundary layer. And that's, again, parameterized by the stochastic or statistically random process. And the missions, they can be linked to these backward trajectories by what's called the STILT footprint. In other words, it's kind of a weighted probability of uplift of dust sources in the domain. So for this study, we looked at 6 different receptor sites. They each are correlated. These are depicted by the stars. And they're each correlated with DAQ monitors, or PM2.5 monitors. These are going to be compared on an hourly basis. And this is kind of how we're going to validate the model. And we're going to be looking at a particular dust storm event in March of 2010, where the PM2.5 concentrations well exceeded 200 micrograms. And the first attempt at this, wasn't very good. So the black line represents the observations, basically what we saw at Hawthorne and Salt Lake City. And the red line depicts the model concentrations. Now, obviously, as you can tell, it's useless. So the correlation between the modeling and the observations is so bad that I guess we can say the correlation is, well, yuck, right? So kind of moving on, what can we do to actually improve the model? And you look at the 6 other sites, or the 5 other sites along with Salt Lake City, and averaged over the episode, you see that the performance was just terrible everywhere. These green bars, which represent the model average, versus the observations, it's a very poor agreement. Very bad. But as discouraging as that is, we must make progress. We must move forward. So one of the reasons why this wasn't successful is if you look on the left-hand panel, you can see like where STILT sees this dust is kind of to the west, right? Kind of like you imagine the salt flats and all that. And what's actually being fed into the model is not that. It's actually the dust is more located to the south, as depicted in the right-hand panel. So we missed it. So what can we do about this? Well, the one thing we can do, of course, is improve the soil type, the soil distribution. The default model had a really simplistic view of the soil type. It was either silty clay or it was nothing, right? And so basically, we can see the lake here. That's kind of representing most of the water. And One thing that we did was we actually were able to take a lot of this silty clay and replace it with playa, which is much more realistic. And this was done with the National Land Cover Database satellite imagery from 2006. Now, the good thing about playa is that it has lower threshold frictional velocity, so it's not going to take that much more wind to kick it up and transport it places. So again, looking at where we were before, where we started from, not very good. But once we made the improvement, bam, all of a sudden now we're starting to see the dust. Now we're starting to see it come into the Salt Lake City. And that's what you see here about the magnitude here. A pretty good response here. There's a little bit of a lag in the onset of the event, but overall the magnitude's captured really well. So going from the green bars where we were originally to the red bars, this is quite an improvement, and it represents a much better agreement with observations at all 6 sites. So another thing that we did was actually we looked at the bathymetry data from the U.S. Geological Survey. And bathymetry, what that represents is kind of just the height or the depth of the water at basically every point in the Salt Lake. So this is very high resolution data. And this would help improve the modeling as well, as we'll see later. But on the left-hand side, that's kind of where we were, and we just kind of showed that. The red is the playa, the yellow is kind of the silty clay substance, which isn't quite as we're not quite as able to transport that as we'd like. And then there's the Salt Lake. So if we were to, remember I referred to the Bear River earlier, and if we were to actually dam that river, then the red represents what would be kind of just newly exposed lake bed. And assumption here is that it would be very, very subject to being lifted up. And so we represent that as kind of more or less playa around the eastern bench. You can actually look at the eastern side of the lake and you can see that, just kind of comparing the two images, that, this is quite a lot of more exposed lake bed. And hence probably, a lot more dust, you'd think. So the third scenario we looked at is we actually completely removed the Salt Lake and replaced it with playa. So what would happen with dust here? So this is kind of 2 different sensitivities we're going to run, and we're going to see basically what happens. So again, here we are originally where we were able to kind of show that the model, it's room for improvement, but it's working okay, at least as far as capturing that peak concentration for that 1 hour. Now, if we were to actually dam the Bear River, this is kind of what the model's telling us by the purple line. So not only are we seeing just much more PM2.5 accumulated, but we're also seeing kind of a longer event, They're just kind of represented by that kind of secondary peak right there. Now, what happens once we actually remove all the water in the Great Salt Lake? Well, then we get a really big peak, a secondary peak that's almost as big in magnitude as the first peak. So about 200 micrograms. And in other words, through the duration of this episode, we've more than doubled the amount of dust coming into Salt Lake City. So looking at the 6 different sites, of course, I guess there's 5 depicted here, but they're not all of them obviously responded the same way as Salt Lake City. For example, Logan, just because of its geographical location, obviously wasn't impacted as much by removing the water in the Great Salt Lake as, say, Ogden or Salt Lake City was, but there was some impact nonetheless. And for this event, we would estimate, or we'd simulate 75% more dust at Logan, and again, about over 100% more dust in Salt Lake City. And but even just damming the Bear River, you can see that actually has a big impact on terms of how much more dust we'd see during this particular event. So the conclusion, we were able to kind of test this model and kind of see see that it works, and we were actually able to evaluate some impacts, environmental impacts from A, damming the Bear River, and B, kind of a more unrealistic but kind of a post-op well, you know what I'm saying, scenario where kind of a scenario where there's no water in the Great Salt Lake at all. So again, a 2-fold increase in Salt Lake City and PM2.5 during this one event. And even this minimal decreases on water levels, such as, again, just damming the Bear River, that had a big impact. So what's next? I think that what's next is we actually need to run more episodes. It's not enough just to run one episode and claim that we know all there is to know about these kind of impacts. We need to do more work. The second thing that's important to repeat is that it's not only the magnitude, but it's the frequency of the events. As the water level diminishes in the Great Salt Lake, we should probably expect more dust events. And that's it. So I'd like to acknowledge the Friends of Great Salt Lake and the, that's better. So Utah Department of Environmental Quality. So thank you.